Okay, so maybe I should. I want to add something to. Okay, we started with F. That's not very good. We started with F, so we support of F that took some S. So first thing which we can do, we can find some open subset U which contains this S and doesn't contain other things that support. So we can assume that support of so first we stick this F to this U. So then the claim is that this will be still irreducible. H equal F restricted to U is irreducible. And F is equal J star shriek of H. So why this is correct? Because we have just morphism from so F is restricted to U. We map. So why H is irreducible? Suppose H has some. Suppose H has some quotient H prime. So then we get non-trivial morphism F restricted U to H prime, which means we get non-trivial morphism from F into J star of H prime. And yes, and since F is irreducible, this morphism will be an embedding. I can assume that J is affine. So then this morphism will be embedding. And yes, but we assume that H has some quotient. Yes, so this will be embedding, so it will be embedding on U. But on U, we assume this will be morphism from H to H prime. So we see that any quotient morphism is in fact an embedding, so which means that H is irreducible. So in this way we can okay, so this means that H is irreducible. Now why F is equal to this? So the idea is very simple. So what is J shriek star of something of H? So I defined it as a image of J shriek of H in J star of H. But you can see immediately what does it mean. This means that it is a submodel of J star of H. It can be characterized as submodel of H star of H, such that quotient has support outside of U. So hence, if I have morphism F restricted to U here, then I have morphism of F here. But I claim that if F is irreducible and then it doesn't have any morphism into any model which has support outside of U. Because, so claim, if R is perverse and support of R lies in X minus U, then whom Fr is equal to 0. Because any morphism from F to I will be embedding, because F is reusable. If it is embedding, it should be embedding everywhere, in particular on U. But on U, this is equal to 0, R. And F is not equal to 0. Okay, so that's how, so we actually use the fact that not the characterization of this is a, if you want, maximal submodule here, such that, or minimal submodule here, such that quotient is supported outside of U. That's another characterization. Okay, so in this way we use this to the case when F is just that support of F, so reduced to the case when support of F is equal to S is closed in U. We can replace X by U and reduce to this case. Now we know that if you have perverse sheaves which are supported on closed subset are the same as perverse sheaves on this subset. So you can assume that F just lives on this subset. On closed subset are the same as just perverse sheaves on this subset. Okay, so and we, since we, from the very beginning we could squeeze S a little bit and take corresponding Q, so we can assume that F is restricted to S, that I shriek. So in this case, I shriek is equal to I star of F. Will be some, I don't know, M on S, and we can assume that it's local system. Because otherwise we could squeeze M. Okay, and then the same which we before we take, I don't remember, is a usable subsystem here or a usable quotient, and it just repeats the same thing. Okay, so now I want to give some characterization of reducible perverse sheaves. This is standard notation. So if you have S in X and you have, for instance, L local system on X. Yes.
Make sense to myself. So the case S is closed was discussed in the end of last class.
Yes.
And what you just explained, the reduction from the general case to the case that S is closed.
Yes.
Okay. This is what was.
Yes. So we can assume that S is closed, and moreover, when you stick F to S, you'll get this local system.
Sorry, this is additional.
Yes.
We assumed earlier.
Yes.
Okay.
So then, if this local system turns out to be not reusable, you consider it's reusable sub quotient and repeat the same argument and see that it's.
So it simultaneously proves the 1 and 2 and all the reducibilities and simplicity of things in the middle.
No, so the claim is that if support of F is closed smooth subvariety, and the section of f to this subvariety is local system, then this local system is reducible. That's the statement. Okay, that's the same. So, there are several standard notations. So I denoted L of S E. This is irreducible. Perverse sheaf. Now,
epsilon instead of L and on S?
Excuse me. It's not epsilon, it's E. And local system I usually denote by E.
And on S, right?
On S, yes, you're correct. Up to these model summations. Okay, just so the standard, in case when local system is trivial, there is standard notation for this, which is called IC sheaf of S. So by definition, it's L of S local system, trivial local system, CS. Okay, so I don't know whether there is a standard notation ICSE.
No.
Probably. I don't know. We can introduce this notation. Okay, so now I want to give some. Let me remind what was characterization of perverse sheaves, and give similar characterization of IC sheaves. So IC sheaves, these are just irreducible perverse sheaves. IC sheaves is more general. Okay, so let me define that. So F D. So F is constructible. F is perverse. So what was the condition? It was a pretty complicated condition. So it can be formulated in several different ways, but if there exists stratification, S collection of Si, where we assume the dimension of Si is equal to I, and they are smooth and all these things, such that first for any point x in Si, Ix star of F is concentrated in degrees more or equal to I. And the second condition, Ix sheik of F is concentrated in degrees less or equal minus Ix. And here less or equal to I.
The other inequality.
Yes, less or equal to minus I, yes, okay. And here is more equal to I. Okay, and so the claim is easy to show that F is IC sheaf. F is, so if F is IC sheaf, then you have very similar inequalities, but slightly you have the same kind of inequalities, IC sheaf corresponding to S. So then you would have that Ix star of F will be less or equal minus I minus 1 for all x not in S. And similarly the second one. More equal I plus 1. All x not in S. So on all smaller strata, so it is, so you have, so this thing will be concentrated on closure of S. And the condition is that on all smaller strata you have, on this strata you have exactly this condition. But on all smaller strata you have slightly stronger condition, just one. And this is more or less obvious that it's correct because in both directions, for example, if for some strata you have you have here, for instance, equal exactly minus I, then this means that you take this minus, you stick to this strata, you consider this minus I part, this is some local system, and then you just have morphism of your sheaf into the restriction of your sheaf into this local system. And by duality, it means that you have morphism of F into image of this local system, which is impossible because F is reducible.
In general, you have this highest cohomology allowed. This sequence of cohomologies tells you the Job-Holder sequence of the module or something like that? The Perverse.
Yes, no, more precisely. Maximal tells you if you have, okay, so the claim is that if at some moment you have on some strata, you have element of cohomology on maximal possible degree, then this means that you have there exists in Jordan curvature, there exists piece which corresponds to this strata.
Maybe I don't understand something.
Yes.
But do you assume anything about S here, for instance? Because because if you take just a line,
Yes.
and S is everything minus a point,
Yes.
and they take just the trivial intersection cohomology sheaf from
Yes.
everything minus a point to everything, then there is no extra drop at 0. Yes, if 0 is not in S.
Yes.
But the I star is not extra.
No, it is because now you're living on strata of smaller dimension. I is smaller now.
Okay, so
So you have.
I see. Okay.
Okay. No. Okay. So this is just easy again. This easy checkup, but from here follows some interesting phenomena that sometimes in some rare cases, but which are very useful, you can claim that some perverse sheaves are irreducible. Namely, let's select pi xy be a proper morphism. And let x be smooth. So this is a standard situation when we try to resolve singularities. So we say that pi is small if it has fibers of small dimensions. I will write in a moment. So the claim is that so if pi is small, then direct image of some log ICX, for example, is irreducible. Irreducible perverse sheaf.
What do you mean by small dimension?
Okay. So let me say, so situation to which we consider this will be that x and y have the same dimension. So generically, you have just one or finite number of points in pre-image. At some points, you have some variety of larger dimension and so on. But the claim is that each time the dimension is not very large. So how to state it is the following, that you just say that. So I want to write down what this condition, what does it mean, small morphism. So you can, yes, I will move to the left. So what does it mean that pi is small? So once more, this is just condition on dimensions of fibers. They're somehow not large. Again, it can be written several different forms, but let's, so pi is small means one of the exists a stratification Si such that for points x in Si, so dimension of Si is equal to I. Dimension of fiber is less or equal to, I think, codimension of Si in X. X twice codimension.
Dimension in Y?
To Y.
In S is stratification of X, of Y, stratification of Y, of Si in Y. So, okay, so what does it mean? This means that for the generic point, the dimension of fiber is 0. Now, okay, so now there are two notions of small and semi-small. But semi-small is a little bit easier. Then for generic point, it is of dimension less or equal to 0. For codimension 1, it is dimension less or equal to, I don't know, just, no. So, okay, so twice dimension. This is less or equal dimensions. Okay, so let me explain. Okay, I never remember this thing. So the idea is very simple, that we would like to consider, for instance, O of x, not O of x, that the constant shift of x shifted by by dimension of x. So this ICX. They would like to consider its direct image. So I want to show that this is a perverse sheaf. So how I show this? That I should show that it satisfies all the conditions. So I want to take some point x, and I want to take Ix star of this. It's not H of H. But since pi starts coincide with pi shriek, then by base change, this will be nothing else than cohomologies of pi minus 1 of x with coefficient and constant sheaf. So now we just require that these cohomologies don't are zero in sufficiently high dimensions.
This
So-
being small x.
Hmm?
This being fiber over the point x.
Yes, this is pi minus 1 of small x, yes. So fx is equal to pi minus 1 of. So you can see the fiber, and we want to guarantee that cohomologies are not if small dimension. So
Do some kind of proper base change or something like that?
yes, no, it's just base change. So in this thing, there is no proper base change. It's just base change. That's it.
The dimension
So-
shift. You had a dimension shift up the stairs. Did you disappear or?
No. So first I want to find what's semi-small.
No, I mean here you had f is cx shifted by dx, and in your formula below it's not shifted anymore. Is this intentional?
No. So this still shifted by dimension of x. I think that's why here you will get codimension all the time. Okay, so the idea is that the claim is that if this variety has small dimension, then its cohomologies are automatically zero. So this is hi of pi minus 1 of x is equal to 0 if I is more than twice dimension pi minus 1 of x. Because you have complex variety. So this is just condition. So now you impose such conditions to guarantee that the image will be perverse sheaf. So the claim is that if you have semi-small resolution, then direct image of IC sheaf on X will be perverse sheaf downstairs. Just a stupid computation. And now the claim is that if you consider slightly more restrictive condition, then you'll get the direct image will be in fact a reusable sheaf, perverse sheaf.
Since the fibers are fine, you get the same effect by assuming without the two. Is that correct?
No. In this case, you cannot.
You cannot.
No, the idea is that I do it for pi star, but then by duality I can do it by pi shriek. So and for this I need proper. So this works only for proper things. Okay, so there is notion of small and semi-small, and again, so yes. And so the claim is that if morphism is small, then it maps pi low shriek, which is the same as pi low star, maps perverse sheaves to perverse sheaves. If it is semi-small, if it is small, then it maps ICX into reducible.
What is ICX?
ICX, which is reducible sheaf, which corresponds to X.
Just to X.
Yes. To X and in fact to any local system on X. It's just so once more, this is just these very trivial computations. Okay, and now I want to explain why this is very useful. I want to explain this, how this implies the following construction, which was invented by Lustig. So construction.
Really apologize for being.
Yes.
Did we say what small is? I couldn't get it.
So small is some conditional fibers, which
similar to
guarantees, yes, which at some points you should shift by one, these conditions. Small is slightly stronger than semi-small. For generic points, it is the same as orbit is 0, but on codimension 1, you have still not curves, but points. On codimension 2, you have so you have slightly stronger conditions for all points except on the large strata. Okay, so before any perverse shifts, Springer did the following things. He defined the action of. So suppose you have G's reductive group, a semi-simple complex algebraic group. Then Springer defined for any, if you have U is any unipotent element, he describes Springer fiber, which is considered all Borel subgroups which contain this unipotent element. And the claim, this is some proper algebraic variety, sometimes it is reducible, and what he defines that the while group acts on cohomologies of this Springer fiber. And I would like to describe Lustig's construction, which using perverse shifts explains how to do it. So Springer think was some very non-trivial, use some essentially periodic shifts, and it was so. Okay, so the idea. So the idea is the following: that in general, so suppose they have variety X, and they have some open subset U, and they have L as local system on U. And U is smooth as usual. So then I can consider L. Yes, so then I consider so E shifted by smooth of dimension N. E shifted by N is perverse shift.
L is E, I think. L is E.
Yes, excuse me. Is perverse shift on U. And I can then consider J star shake of this E of M. Okay, that's very nice. Now the idea that this is Factorial operation. So suppose now I have action of some group on this local system. That's what will happen in our case. Then it automatically acts on this guy. In particular, it acts on fibers, or stocks of this guy. And this turns out that this exactly gives Springer type construction. So let me describe. So this general ideology, so let me define. So first of all, there is Grothendieck resolution. You have G is algebraic, reductive algebraic group. Then what is important to know about this? So first of all, there is B is the Flux variety, which consists of all Borel subgroups. It has natural, so So if you have B is one of points here, then you can identify B is equal G mod B. So the group G acts sensitively on this Flux variety. Stationary subgroup of some point is just Borel subgroup corresponding to this point. Okay, so now this Borel subgroup has just a moment. Do I need this? No, probably I don't need this at the moment. Okay, so now there is the following general construction, which is called Grothendieck resolution. Of G. So in principle, G is non-singular, so there's no point constructing resolution of G. But if you consider adjoint action of G, then somehow different points are quite different. So if you would like to resolve this situation, so what we consider G tilde, by definition, it consists of pairs G, B, where G is pointing G, B is pointing Borel subgroup, under conditions G lies in B. No. So this is algebraic variety. You consider product of G times B and consider incidence variety. Okay, so now what do you have here? You have natural projections, G tilde into G and G tilde into B. B, excuse me. Now, G tilde. Now, this morphism is fibration, which fiber at every point is just B. For this reason, this non-singular variety, this non-singular variety and fibers are non-singular variety, so this non-singular variety. So in a sense, this is resolution. Now, what is this morphism? So to each point GB, we assign point G. So let's consider fibers of this morphism. Let's consider just element. So it is, let's consider element G in G, and let's look what are Borel subgroups which contain this element. So the claim is that if your element G is regular semi-simple, then it generates, what does it mean it's regular semi-simple? It means that it generates Cartan subgroup. And then there are W Borel subgroups which contain this element. So fiber, so if G is regular semi-simple, then there exists W Borel subgroups containing this element G. In fact, more is true. It's not just W, number W, it's related to W, namely the fact, the claim is that this abstract group W acts on this set, simply transitively. There's canonical action of this set, which is simply transitive action. Now, but if you have some other elements which is not semi-simple, then, for instance, if you have element 1, then it lies on every Borel subgroup, so pre-image will be B. So now it's easy to see that any element you can decompose as product of semi-simple and unipotent, so more or less clear that important things are what's going on with unipotent elements. So if you have U unipotent element, U unipotent, so then you have BU is a set of Borel subgroups that B contains U. It is the same as fixed points of U. Points of U in B. The group G X on B, in particular element U X on B, it has some fixed subvariate. Subvariate of fixed points is the same. So they have different dimensions, and these are just Springer fibers. So the claim is that the group W acts on these Springer fibers. And here's Lucy's construction, how to construct the section. So he says the following. Let's consider IC sheaf on G tilde. So it's just constant shifted by something. And let's consider, let's denote this pi, this morphism. This morphism is proper because the rate B is projective. And this G tilde is close subvariate in G cross B. And let's consider F, which is pi star of IC of. So now the claim is that morphism pi is small. So this you just check by using this thing which I described. You just check that fibers have sufficiently small dimension. So hence F is reusable. Now consider in F is sheaf is perverse sheaf on G. Now consider in G we have subset of G regular semi-simple. Let's note it U. Let's consider F is equal to U.
Maybe W.
Definitely W is.
Oh,
Why U is not good?
unimportant.
U is sometimes important. Let's note G regular, just without U. So of U, so P minus 1 of G regular into G regular is covering, which I explained, with action of the group W, simply transitive action of the group W. This means that F is equal to G regular has canonical action of W with Y group. So on the other hand, just one moment. So, what?
The one containing that element.
So what is the question?
It's
So why is the group WX?
No, there seems to be a bundle of groups, right?
Okay, so
Right.
let me finish, then I will explain, because there is some very nice construction which is useful to know anyway. But I want to explain thing here. So it's not correct that F is reducible. It is so the idea is that it's all its reusable components have full support. There are no embedded components. So the idea is that in order to something to be, so in one direction, if you have IC sheaves, then we have seen that it satisfies some conditions. Conversely, if sheaves satisfy some conditions, then it doesn't mean that it's reusable, because, for instance, direct sum of several sheaves will have the same condition. but it just means that it doesn't have submodels which are concentrated in smaller dimension. Okay, that's better. Just what I want to say is that from all these things follows that F is just J star Schlick, so J is embedding, this embedding. Of F restricted to G regular. So this condition on fibers will imply that F, which F is just direct image from upstairs. The claim is that it's, if you restrict it to G regular, it becomes local system, which you understand. And the claim is that it will be just equal to this extension, Schlick star extension of this local system. Now, on this local system, we know action of this group W. Hence, here we also know action of the group. We have action of the group W because this operation is okay. And now, so hence on every fiber, on every fiber of F for any point G in G. So you have that on cohomology for this fiber, action of W. And these fibers are exactly this. If G is unipotent, this will be exactly Springer fiber. So in this way, so the language of perverse sheaves allows immediately describes that there is some action of W. So say, in substance, you analytically continue. You have action on the regular semi-simple elements, and that you can analytically continue as fibers at every point. How to then analyze this and so on, that's different story. So we define, so there is some action. What can you tell about this action? That's different story. For instance, let's say, this is just the Springer correspondence. So in particular, for instance, you can consider, if you consider some BU, U is important, then it usually is it usually has several components, often has several components. Now one can show that all components have the same dimension. So the intersection is dimension K. Then the most interesting is action of group W on the cohomology H2K of BU. So just highest cohomologies. Okay, so this is called Springer representation, and Springer has shown that more or less all representations with group W you can realize in this way. But once more, important thing that in this way you can construct action of W on these cohomologies which you don't see geometrically at all. Okay, next time I explain, but when you use trivial, how you can see geometrically this action, but in general, not clear.